So let's do a quick lecture review at this point before we move back into the rest of it. Inertia is a tendency to retain motion, or resistance to change of motion. Tendency to retain motion or the resistance to change of motion in the absence of an external force. In the absence of an external force, it's either the tendency to retain motion or the resistance to change of motion. Motion means velocity, so velocity is a combination of speed and direction. So what that means is in the absence of a net external force, if you're moving to begin with, you're going to keep on moving in a straight line at a constant speed. Or if you're at rest, you're going to remain at rest. Inertia is also known as the Newton's first law. It's the same thing. So where do you get that tendency from, or the resistance to change of motion from? You get it from mass, guys. Mass is the measured inertia. Measure of inertia becomes your mass. So the proper unit of mass, so mass and inertia, they mean the same thing. It's going to be kilograms. In the United States, we use pounds. The second law says if there's a force, it overcomes the inertia, which means that it changes your speed, the direction of that speed. It causes acceleration. All right, notice that you got these arrows, which means that they're vectors. They will be pointing in the same direction. Force and acceleration will be in the same direction. Acceleration is going to be caused by a force. Proper unit is newtons. In the United States, we use pounds. All right. If something is speeding up, is there enough force acting on it? Absolutely, because it's accelerating. All right, so which means that it's accelerating. If something is slowing down, is there enough force acting on it? Absolutely, because slowing down is acceleration, so it's accelerating. If something is moving on a curve at a constant speed, is there enough force acting on it? Yeah, it's moving at constant speed, but it's moving on a curve, so which means that it's changing direction. That implies that it's accelerating. If it's accelerating, there's enough force acting on it. All right, so Newton's third law is an extension of the first two. Newton came up with the third law to actually provide an explanation as to how these forces in nature come into existence. According to Newton, for every single action force, Fa, there's going to be an equal and opposite reaction force, which is going to be Fr. All right, so they will have equal magnitudes. Magnitude is going to be the same, which means that these forces are going to have the same sizes, and they will be pointing in opposite directions. Because they're applied to two different masses, they will never cancel. All right, so head-on collision between a car and an SUV, right, which one experiences a large impact force? Same, according to Newton's third law. If that's the case, why is it that the damage suffered by the car is significantly larger than the amount of damage by the SUV? Well, they will share the same force, which means that they will both experience the same force. And the acceleration is going to depend on the mass. The vehicle with the smaller mass is going to suffer larger acceleration, suffer from larger acceleration. All right. So smaller mass is going to experience more acceleration. So acceleration is what actually causes the damage. What maims you, what kills you, what breaks your bones. You can do an extreme. We got a person in front of the train getting hit by a train by 500 million pounds of force. So does the person apply the same force back on the train? Answer to that question, once again, is yes, according to Newton's third law. If that's the case, where's the evidence? Where's the evidence that the person applies the same force? Evidence is not very visible in this case. All right, the bigger the mass is, the smaller the acceleration is. So your life, actually, your presence in front of the train is only going to cause a very small amount of vibration on the train. Acceleration of the train is going to be unnoticeably small. It's just a vibration, guys. The train is going to go from 60 to 59.999 miles per hour within a fraction of a second. So that's the extent of the damage that you're going to have on the train, which is just a simple vibration. What's the net force? Some total of all forces acting on a system. Direction is going to matter. To the right, positive. To the left is going to be negative. All right, so you can sum up the forces along the x direction, y direction, or z direction. And net force is what's responsible for the acceleration of that system. Okay, so moving forward, so the car is fixed. So you're taking the car out for a spin. You're taking it out for a test. We're going at 73.5 miles per hour at this point. All right. Now, here's your drive force. Here's the opposing force, the frictional force, right? All right. Notice that they're equal in magnitude and opposite in direction. If that's the case, what's the net force acting on the car? Right, so we're not going to do it mathematically because it's so obvious that you don't have to. All right, you got two forces, opposite directions, same magnitude, acting on the same mass. It will cancel, guys. They add up to zero. That's what it means. If that's the case, what's the acceleration? Zero. If that's the case, how fast do you think the car is going to be moving? About 10 minutes later, 5 minutes later, it's going to be the same speed. It's about 73.5 miles per hour. All right, so what if when you're going about 73.5 miles per hour, what if there's some kind of mechanical engine failure, engine breaks down, then what happens? What happens to the car? Has this ever happened to you? You're driving on a highway, going around 70, 80, 90 miles per hour, and then boom, the engine cuts off. All right, so race, I'm going to give you 5 points. It's absolutely, that's exactly what I thought. All right, so 20 years ago, I started working in an art school. And this school had two campuses, one in Schaumburg, which is a suburb of Chicago. And the main campus was located in Chicago, downtown Chicago. So on a given day, I had to split my time between these two campuses. They're like 32 miles apart. And then you would have about an hour to just change campuses. So it's heavy traffic or whatnot. So one day I'm going to Chicago after the lecture. And I'm driving my Ford Tampa. Ford Tampa is an interesting car. It's a really cheap car. It was also really, really sturdy. I got to tell you, I forgot to change the oil for a few years. And then the engine almost caught fire. And the car still worked after that. That was humongous. So speedometer would go up like 90 miles per hour. The car would not go any faster than 75. Imagine that. So I'm just trying to make up time on the highway. So I'm going at 65 miles per hour. Not fast enough. Went up to 70. Still not fast enough. I know I can get it up to 75. But once you hit like 73, usually it's a struggle. So finally I get up to 73. And then car did something that never did happen before. It started shaking violently sideways. So this thing is shaking, and all of a sudden, boom, the door pops open. I shut the door, lock the door, and now I'm struggling. I'm just trying to get the car up to 75 miles per hour. I know we can't do it. So the vibrations started to intensify, and then boom, the engine cut off. So what happens when the engine cuts off? Number one, it should never happen. And if it does, it's not what you think it is. The first thing that happened was the steering wheel locked up on me. No good. And the next thing I know, I'm just going to put the brakes on somehow, which I've applied the brakes, obviously. Nope, no brakes, no steering wheel. And I'm going at 73.5 miles per hour, guys, on a highway. All right, so what does that feel like? You're thinking it feels pure panic. And is there anything that I could have done? You're thinking that emergency brakes, I got news for you. Unknowingly, I was evidently driving the car on emergency brakes for about 6 months, so there were no emergency brakes either. All right, so I'm going down the highway, no control over the car. It's like a missile at 75 miles, 73.5 miles per hour. So what am I thinking? I'm thinking, I think I'm going to die. There's no other way out. And then I thought to myself, what's the big deal? Everyone is going to die one day, right? So I might as well take a couple of people with me. Except the car came to a stop pretty darn fast. So what happened was, when the engine ended up getting cut off, it generated a tremendous amount of friction. In fact, the car came to a stop within about 1,000 feet. And then I was able to push the car off the road. All right. So I'm going to take that as an example, a car engine cutting off and the car coming to a stop. And then we're going to try to figure out how long it takes for the car to come to a stop. All right, so in terms of seconds. All right, so initially the car was going at 73.5 miles per hour, give and take. When the engine cuts off, what happens? The only force acting is friction. And then the car is moving horizontally about 1,000 feet. So my question is, how long would that take for it to come to a stop? Right, so one of the things that I notice is once the engine cuts up, it generates a tremendous amount of friction at that point. I mean, you got the surface friction, but also the friction generated by the rest of the car. All right, so, okay, I gotta see this. I can barely see this. Let's move. All right, so we're going at 73.5 miles per hour, and we're slowing down to a stop within a distance of 1,000 feet. So determine the friction is the only force acting on the car. So this is 73.5 miles per hour. A tremendous amount of frictional force acting on the car. I think this is a little bit more friction than the car had at the time. So what's the net force in terms of newtons and pounds? What's the acceleration? And the amount of time it takes for it to stop. Okay, the weird stuff about this problem is mathematically this one is the easiest one, and for whatever reason, this is the most confusing one for most of you guys, because if you're watching this, you almost feel like you can handle it. Okay, and except when you have one single force, it causes all sorts of confusions. I'm not sure why. Miles per hour to meters per second, feet to meters. Those are the conversions. You need pounds to newtons, so that needs to be done. All right, miles per hour to meters per second, obviously, is whatever we had before, 32.8 meters per second. 1,000 feet to meters. It's going to give you about 300 meters. And this is going to require a little bit of finessing because this is a new concept. So you're going from pounds to newtons. So roughly about 10 newtons is going to be 2.2 pounds. Stuff that we did learn last week. All right, so we're done with the conversions. All right, so what's the net force? Net force is just the single force acting in the opposite direction of motion. Motion is forward. So net force is going to be the negative of the frictional force. That's it. Okay, there's nothing complicated about it. All right, so we're following the same format, except I'm getting rid of my lines. I'm getting rid of the lines, so which means that we're actually doing the same problem without the training wheels on. All right, so frictional force is going to be 8,000 newtons. Okay, I'm going to make a correction there soon. I end up losing a 0. All right, so the net force is what causes acceleration. All right, so it's going to be 8,000 divided by the mass of the car, which is going to be 2,000. All right, so 8,000, I made the corrections. So that's going to give you 4 meters per second squared. acceleration. It's almost like the brakes locked up. This is kind of weird. This is a huge acceleration in reality when the engine cut off. All right, so the next question is the amount of time it takes for it to come to a stop. Okay, here you guys will have to start providing justifications starting with next week. You got this formula has got time in it. This formula has time in it, so is this one. Which one do you use and why? You can only use this one if you have a variable acceleration, which means that's jerking motion. All right, this formula is available if the motion is jerking motion. Car is slowing down, but it's just vibrating. That's the sort of stuff. If it's a uniform acceleration, if it's uniformly coming to a stop, and you got these two options. All right, so those are the only two options available for you to be able to use. Hey, thank you. Awesome. All right, so these different formulas mean different things. So as long as you say, I'm using this, I'm assuming that this is a variable acceleration. When you put the brakes on, car jerks a little bit. Okay, that's your assumption. All right, I'm not gonna, because when you're solving a problem, you gotta make assumptions. Then you pick this one. You assume that it's just smooth, it's just coming to a stop in a very predictable sort of way. Then you got these three formulas available to you. So you will get graded on the assumptions that you're making, the justification of the assumptions in this case. All right, so I will assume that this is a uniform acceleration. Right? There's no jerking amount. Somehow the engine cuts up, and the car starts to slow down in a very predictable, uniform sort of way. So I'm going to pick this formula. The car is already moving at 73.5 miles per hour. You get a huge acceleration, is 4 meters per second squared. It'll come to a stop. The final speed is going to be 0. All right, so figure out. Okay. I've been seeing this just about every time I solve the problem. I don't know if we are up to 20, 25, or 30 problems already. Notice that the patterns are always the same. I always say the same thing. Don't use numbers, don't use numbers, don't use numbers when you do your algebra. And maybe I'm hoping that for those of you guys who are really good selective listening, you are hearing me the first time. I'm hoping that at this point, because we're doing it for almost a month, you go, wait a minute, this guy wants us to do it in a certain way. Yes, I do. I've been saying it all along. Because I don't really like to write a lot of stuff that you're not going to read. I'd much rather just keep telling you. And hopefully while you're either watching the lecture, you go, oh, yeah, that's exactly what this guy's looking for. Because all these tests so far are formatting tests. And you guys are thinking, wait a minute, I get the right answer. Why did I lose 90% of the points? Because you get graded on how you get to the solution. I just want to make sure that you get to the solution by showing your work step by step by step by step. It's a discipline. It's a way of solving a problem. Is how you get graded. It's not because you get a certain number. It's not multiple choice. Showing work means make sure that everything is in the right units before you start. So you don't have to worry about, oh, I wonder if I need to convert this to this and that. It makes it really complicated. And clear separation between the numbers and the solution, the algebra. And then you keep the algebra really clean of the numbers so I can see the work. Because you're trying to make a point, you're trying to emphasize a point there. It needs to be 100% clean. The only thing that you can put in is zeros because it's only going to simplify the algebra. Not the other numbers. I don't carry my 4 over. I don't carry any of the numbers. I don't degrade my solution by putting numbers in it. Let me put it this way. Keep it in the pure symbolic form. And you will thank me later if you become a physicist or engineer or whatever, because no one is going to want to see numbers in your solutions. No one has that kind of time. Because normally when I look at your solution, it takes me 15 seconds to grade this stuff. 15 seconds. I look, I say, okay, everything is there. I can see your assumptions. I can see that you're either justifying it or you're not justifying it. Based on that, I can make my deductions immediately. So the final answer is going to be 0. I show a lot of work here. Normally, you don't have to show this amount of work. But you need to pick a formula, which is a standard formula from the formula sheet. And then starting with next week, you have to justify it. Because now you have to pick and choose formulas based on your understanding of physics. So T and boom, 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 here's the final equation. And this is the final equation that's going to take the numbers in. So your initial speed is going to be that number. Your acceleration was, what is it, 4. It's going to give you about 8 seconds. All right, this is fairly